Hi, my name is William Krause, and I will be presenting on magnetic levitation. So, magnetic levitation in this experiment is created by the attraction of two magnets, a lifter electromagnet and a levitating magnet, and the repulsion of a diamagnetic apparatus to cancel out the attraction and to create conditions for stable magnetic levitation. The main focus here is diamagnetic materials. So, diamagnetic materials generate weak magnetic fields that oppose externally applied magnetic fields. And the strength of these magnets are characterized by magnetic susceptibility, which diamagnets are negative. The main focus of this experiment was to calculate the magnetic susceptibility of bismuth and pyrolytic graphite, which are both diamagnetic materials, using stable levitation, interplate distances, and a driving frequency at which the lifter magnets oscillate within the diamagnetic apparatus. So for this part of the experiment, the lifter electromagnet is driven by a function generator, as you can see here, to cause the levitating magnet inside here to oscillate. So there is attraction between this levitating magnet and the lifter electromagnet, and which is then repulsed by the apparatus here, and then the function generator supplies a frequency to then cause this magnet to oscillate. And the screw at the top of the apparatus is used to increase or decrease the interplate spacing here, which is denoted D. By changing this distance, we can then find the oscillation frequency at which the magnet will oscillate with the most amplitude. And the dial here is what changes the frequency. So here are results. So here you can see our data for the interplate distance versus the oscillation frequency, where we took 7 trials varying distance and then supplying certain frequencies that would cause oscillation with the most amplitude. So the top equation here is the plate spacing frequency equation to calculate our chi, which we use to fit the curve to our graphs and our data, where M is, big M here is the dipole moment of the small levitating magnet. Little m is mass, and mu naught is the vacuum permeability, and D is the interplate distance of the apparatus. ML here is the lifter magnet dipole moment, and H is the effective dipole-dipole separation, which is calculated by using these distances H1 and H2 here, and then using these equations here. So here's our analysis. Graph 1 is the frequency versus interplate distances for the bismuth apparatus. And then here is the same for the pyrolytic graphite apparatus. And from our calculations from the first plot, the magnetic susceptibility of bismuth was found to be negative 121 times 10 negative 6 plus or minus 112 times 10 to the negative 7. And pyrolytic graphite was found to be negative 120 times 10 to the negative 6 plus or minus 100 times 10 to the negative 7. And this, just looking at the graphs, you can tell that they should be around the same value because they followed the same kind of relationship. Obviously, the graph here is kind of missing the lower interplate distance, but it should be around the same oscillation frequency, following the same sort of pattern. So these results here are proven by the relationships you can see here. But this should not be the case, and this was not what we expected. And this is why. The theoretical chi for bismuth, it was negative 170 times 10 negative 6 meters cubed per kilogram, but which is not that far off from our experimental here. But the pyrolytic graphite shows a huge error, with theoretical being negative 450 times 10 negative 6 meters cubed per kilogram, when what we calculated was negative 120 times 10 to the negative 6 meters cubed per kilogram. So it's major discrepancy, and the calculation of bismuth had a 28.8% error with its chi-squared, or its fit to the data fit to our curve was an extremely low value, showing an extremely good fit of 1.49 times 10 negative 5, but the calculation of pyrolytic graphite had a 73.3% error, and still its chi-squared, or the fit, was extremely low, meaning a really good fit. And the errors in these values we thought to be due to the fact that for this experiment, the precision of our measurement was highly dependable on the precision of our eyes. So we had to manually see and estimate which frequency drove the magnet to oscillate with the most magnitude. But specifically for the calculation of the driving frequency for the pyrolytic graphite, the oscilloscope was actually unable to calculate automatically frequencies below 2 hertz. So to make up for this, we had to use the time cursors to manually determine the frequency. The combination of this and the errors stated before would cause major errors in our calculations. So what is the significance of studying diamagnetism? So studying diamagnetism helps us in understanding how materials interact with magnetic fields, and these materials are crucial to creating levitating systems. And through this experiment, we were able to measure magnetic susceptibility of both bismuth and pyrolytic graphite through oscillation frequency of a small levitating magnet and its inner plate distance. And through this lab, we gained deeper insight into diamagnetic materials and a somewhat understanding of diamagnetic materials and their properties. We developed proficiency in Python coding. We were able to enhance our data analysis skills to identify relationships and understand the significance of our experiments. And we were able to improve our report writing and our presentation abilities. And finally, we were able to gain valuable laboratory skills related to experimental procedures. And that is all. Thank you.